morning, students. This is the lecture number 8 on the series of linear programming. The title of today's lecture is Multiple Solutions. As you have seen in the previous lectures that there are many possibilities for the solution of a linear programming problem. There could be a unique solution, there could be multiple solutions, there could be unbounded solutions, and there could be no solutions. So, today's lecture is focusing on the case where we have multiple solutions, and we will be looking at the comparison between the calculations of the simplex method vis-a-vis with the graphical method. So, the outline of today's talk is as follows. Firstly, I will answer the question that I had posed to you in the lecture number 7, that is the previous lecture, and secondly we will discuss the case of multiple solutions of the linear programming problem. Then we will look at the relationship between the BFS, that is the basic feasible solution, when we are talking about the calculations of the simplex method vis-a-vis the graphical method, and this we will do particularly for the case of the multiple solutions or the alternate solutions. We will do this with the help of an example, and finally I will give you an exercise to solve it. So, if you recall in the previous lecture, that is lecture number 7, I had posed a question, and the question was, what are the differences and the similarities between the calculations of the big M method and the two-phase method for solving a linear programming problem. I am sure you must have tried to answer this question by comparing the calculations of the various iterations or the various tables that you have during the calculations of the big M and the two-phase method. Now, the answer lies in the following. First of all, let us look at what are the similarities, what is the calculations or how they are similar. So, first of all, you must have observed that the row entries corresponding to the constraints of the variables during the iterations or during the tables, they are the same for the big M and the two-phase method. By this I mean the entries which are in the pivot rows and the pivot columns, and also the other rows and the other columns inside the table. They are the same for iteration, for each of the iterations for both of the methods. That is the first similarity. Next, the BFS at each iteration is the same, that is the basic feasible solution for each of the iterations in each of the two methods is the same. And thirdly, the solution obtained by both the methods is same, that is no matter which method you are applying, the final solution that you obtain should be the same. So, these are the similarities between the two methods. Next, let us look at the differences between the two methods. Now, first of all, you will observe that the entries in the top row, that is those entries which are corresponding to the coefficients of the objective function, they are placed on the top row, they are not same. Why is that so? The reason is because in the big M method you have everything in terms of M, and in the two phase method, for the first phase you put aside the original objective function and replace it with the help of a temporary objective function. So, since the objective function has changed, therefore, the coefficients corresponding to the objective function, they have also changed, and that is the reason why the first difference is that the entries corresponding to the coefficient of the objective function in the top row, they are not same. Secondly, the entries in the deviation rows, they are also not same. Why they are not same? Because the entries in the deviation rows, they are obtained from the coefficients of the objective function, and they are subtracting the vector multiplication of the coefficients of the objective function and the various columns. So, therefore, these entries are also different. So, I hope everyone has followed what are the similarities and the differences between the big M and the two phase method. Okay, so, next we also want to look at, after all, what are the advantages of the two phase method over the big M method. And you will observe that there are lesser number of calculations, because in the two phase method the artificial variable, they are dropped. As you have seen that the objective of the first phase in the two phase method is to obtain a readily available BFS, and at the end of the phase 1 you will find that the artificial variables have disappeared from the basis, and since they have disappeared from the basis, that is they are 0, therefore, in the phase 2 we can drop them, and therefore, the calculations will be decreased. So, that is one of the very good advantage of the two phase method over the big M method. So, now let us take an example to understand what happens in the case of a multiple solution in an LP. Now, you will observe that in this example we have maximization of 6x1 plus 4x2, which is subject to 2x1 plus 3x2 less than or equal to 30, 3x1 plus 2x2 less than or equal to 24, and x1 plus x2 greater than or equal to 3, and x1 and x2 should be greater than or equal to 0. Now, without solving this LP, can you tell whether this problem has multiple solutions or not? Just look at the various coefficients and the coefficients of the objective function. Can you see some method by which you can tell that the problem has multiple solutions? Yes, you can. Just look at the slope of the objective function and look at the slope of the various constraints, and you will find that the slope of the second constraint is the same as the slope of the objective function. So, this indicates that the problem has multiple solutions. Now, first of all, let us try to look at the solution using the graphical method. Now, you will see that each of the three constraints can be plotted, as I have explained in the method using the graphical method, and the first two constraints imply that the feasible domain is below the line, whereas in the third constraint applies that the feasible domain is above the constraint. Therefore, the feasible region turns out to be A, the point A, given by 8 comma 10, the point B given by 2.4 and 8.4, the point C given by 8 comma 0, the point D given by 3 comma 0, and the point E given by 0 comma 3. This is the feasible domain of the problem. And what are the solutions of the problem? The solutions of the problem are all points on the line segment joining the points B and C. How is that possible? That is possible because if you evaluate the objective function at the point B and if you evaluate the objective function at the point C, you will find they have the highest objective function value. And in fact, if you evaluate any point on the line segment joining B and C, you will find that also has the same objective function value. Let us try to evaluate all these points A, B, C, D and E. So, let us look at the value of the objective function at each of these vertices A, B, C, D and E. In this table, you will find in the first column mentions the vertices A, B, C, D, E, and in the second column the value of the objective function at each of these points. At A, the value of the objective function is 40, at B it is 48, at C it is 48, at D it is 18, at E it is 12, and this implies that the highest objective function value is being attained at both the points B as well as C. This indicates that the maximum value of the objective function is attained at both the points B and C. Now, if you look at any point P which lies on the line segment joining B and C, this point P will also have an objective function value 48. Why is that so? Let us look at the calculations. Suppose P is any point on the line segment joining B and C, then P can be written as a convex linear combination of the 2 points B and C. That is, mathematically P can be written as lambda times B plus 1 minus lambda times C, and if you multiply lambda with the coordinates of B, the coordinates of B are 2.4 and 8.4. Similarly, the coordinates of C are 8 and 0, and if you multiply lambda times 2.4, 8.4 plus 1 minus lambda times 8, 0, you get a point which is 2.4 times lambda plus 8 times 1 minus lambda, and in the second coordinate you will have 8.4 times lambda. Now, this point P, if you substitute in the objective function, the objective function is nothing but 6x1 plus 4x2. When you substitute this point into the objective function, you get a value 48. This implies that no matter what point P you choose on the line segment between B and C, the value of the objective function will be 48. Please note that the value of lambda should be between 0 and 1. If the value of lambda is 0, then the point B is nothing but the point C, whereas if lambda is equal to 1, then the point B, the point P is nothing but the point B. And for all values of lambda lying between 0 and 1, you will get all points lying on the line segment B and C. And this indicates that not only the points B and C, but also all the points lying on the line segment B and C are the solutions to the LP, because they are having objective function value 48. This is the case of multiple solutions, and now we will look at what happens if we solve this problem with the simplex method. And the objective behind this is to look at the calculations with respect to the basic feasible solution vis-a-vis both the methods. So, in order to solve this problem with the simplex method, we need to write the constraints in this fashion, that is 2x1 plus 3x2 plus x3 is equal to 30, 3x1 plus 2x2 plus x4 is equal to 24, and x1 plus x2 minus x5 plus x6 is equal to 3. I hope everyone has followed that since the third constraint was of the greater than or equal to type, we had to subtract a surplus variable, and since we do not have a basic variable in the third equation, so therefore, we need to add artificial variable which is x6 in the third constraint. Of course, as you know that in the LP in the standard form, the objective function has to be of the maximization type. Also, since x6 is artificial variable, it has to be incorporated into the objective function by multiplying m times x6 and subtracting this term minus m x6. Now, let us look at the calculations. As before, we will look at what is the basis. The basis is nothing but x3, x4 and x6, and this we will write in the first column. Here it is. The first column is x3, x4 and x6. We will write down the x1, x2, x3, x4 and x5 and x6. These entries we will write down from the given problem. 3 2 3 1 3 2 1 1 0 0 0 1 0 0 0 minus 1 0 0 1, and the right hand side is 30 24 3. Also, we will write down the objective function coefficients, that is 6x1. So, from there 6 comes here, 4x1 4 comes here, and similarly 0 0 0 and minus m. So, these are the coefficients of the objective function, and they have to be repeated over the first column over here 0 0 minus m. Now, if you look at this iteration, the initial iteration, you find that the initial BFS, the initial basic feasible solution, is nothing but the basic variables equated to the right hand side. And what does that mean? This means that the initial BFS is nothing but x3 is equal to 30, x4 is equal to 24, x6 is equal to 3, and the remaining variables as 0. So, this is the BFS. You will find that neither x1 nor x2 is appearing in the BFS. Both x1 and x2 are 0. That means that this corresponds to the origin. That is, when we were solving the problem with the help of the graphical method, this initial BFS is corresponding to the origin. And now we want to look at what happens in the next iteration. So, what we will do, as before, we will calculate the deviation rows, and they are calculated like this: 6 minus 0 0 minus m multiplied by 2 3 and 1. So, you will get 6 plus m. Similarly, 4 minus 0 0 minus m multiplied by 3 2 and 1, and you will get 4 plus m. Similarly, 0 minus 0 0 minus m multiplied by 1 0 0, which comes out to be 0. And in fact, I had mentioned earlier also, since x3 is a basic variable, so the coefficient of the deviation row, the entry in the deviation row will also be 0, corresponding to the basic variable. And the same applies for the variable x4 also, because x4 is also a basic variable. So, therefore, this entry in the deviation row becomes 0. The same thing applies for the last variable also, because this is a basic variable. So, therefore, this entry has also to be 0. We need to look at what happens in the x5 variable. In the x5 variable, we have the calculations as 0 minus 0 0 minus m multiplied by 0 0 minus 1, and you get minus m. So, that is the way the entries in the deviation rows is calculated. Now, what is the criteria for finding out which variable should enter the basis? We have to look at the deviation rows, and we find that among the deviation rows, the first entry is the largest, that is 6 plus m. You can compare it with the remaining entries, you will find that 6 plus m is the largest entry, and this indicates that the first variable x1 should enter the basis. Next, we need to decide which is the leaving variable, and for this we will perform the minimum ratio test between the right hand side and the pivot column. So, what do we find? We find that the right hand side is 30, 24, 3, and the pivot column is 2, 3 and 1, and this indicates that 3 upon 1 is the least, because the first one is 30 upon 2, that is 15, second one is 24 upon 3, that is 8, and the third one is 3 upon 1, which is 3. So, this indicates that this variable should leave the basis, okay, and that is the reason why this box 1 is highlighted, and it indicates that at this iteration pivot is the entry 1. Now, since we want to make x1 enter into the basis, therefore, we need to convert this column as 0, 0 and 1. And how are we going to do that? We are going to apply the following elementary row operations, that is, R1 has to be replaced by R1 minus 2 R2, and similarly R3 has to be replaced by R3 minus 2 R2, sorry, R2 minus 3 R3. So, with these elementary row operations, we can make this column as 0, 0 and 1. And what happens when we apply these elementary row operations? Yeah, there you see this column has become 0, 0 and 1. Similarly, of course, the other entries in the in these rows and columns will also change according to the elementary row operations that we have applied. You will observe that this entry was earlier minus m because we had x6 over there, but now since x1 has entered, so we need to change this entry as well. So, this entry has to become 6 because the coefficient of x1 in the objective function is 6. So, therefore, this entry will also change. Next, we need to calculate the deviation rows, and you find the deviation rows are 6 minus 0, 0, 6 multiplied by 0, 0, 1, which is nothing but 0 because it is a basic variable. What are the other basic variables? Yes, x3 is a basic variable, so the corresponding entry is 0. x4 is a basic variable, so the entry corresponding to x4 is also 0. Only entry has to be calculated is for x2, that is 4 minus 0, 0, 6 multiplied by 1 minus 1, 1, which comes out to be minus 2, and similarly corresponding to this variable, that is x5, 0 minus 0, 0, 6 multiplied by this vector, and this comes out to be 6, and the final last column also minus m minus 0, 0, 6 multiplied by minus 2, minus 3 and 1, which comes out to be minus m plus 6. Once these deviation entries are calculated, we need to observe which of them is the largest, and you find 6 is the largest. Please note the last entry is 6 minus m. So, although m is a very large number, but it is appearing with a negative coefficient. So, 6 minus m will be smaller than 6, and this indicates that this variable corresponding to 6, that is the variable x 5, the variable x5 should enter the basis, and the current BFS, if you look at the current BFS, what is the current BFS? The current BFS is x3 is equal to 24, x4 is equal to 15 and x1 is equal to 3 and all others 0. Now, if you look at this BFS carefully, you find that x1 is 3, but what about x2? x2 is not in the basis, so x2 is 0. That means it is corresponding to the point D in the graphical method. So, D is the point 3, 0. Let us go back to the graphical method to see, yeah, here it is. So, the point D is the point 3, 0. You will find that in the initial table we had started from the origin, that is the 0, 0, and immediately after first iteration we have come to the point D, that is 3, 0. This indicates that from the initial iteration to the first iteration we have come to the next point, that is 3, 0. This means that we need to look at the next iteration, and in order to do that we need to calculate the deviation rows, which we have already done. Next we need to look at which is the largest. So, 6 is the largest, therefore, x5 should enter the basis. We also need to see which variable should leave the basis, and in order to see that we need to calculate the minimum ratio test. And what is the minimum ratio test? It is nothing but the ratios of the right hand side with the pivot column. And what are the ratios? The ratios are you find that 24 upon 2 and 15 upon 3. The third one has not to be considered because it is negative, and you find that the second entry is the least. So, this tells us that this variable, that is this variable should leave the basis, and the variable x4 should leave the basis, and the pivot is this box. So, pivot is 3, and we will apply the elementary row operations again in such a way that this vector becomes 0, 1 and 0. So, we want that x5 should become 0, 1, 0. So, what are the elementary row operations that we should apply? Yes, we should apply the following elementary row operations. First of all, the second row should be divided by 3 because the coefficient the pivot is the 3 and we want the pivot to be 1. So, the entry corresponding to the pivot should be 1, and in fact we need to multiply the entire row by the scalar 3. So, that is why this elementary row operation tells us R2 has to be replaced by 1 upon 3 R2. Next comes the elementary row operation R1. R1 has to be replaced by minus R1 minus 2 R2. R1 has to be replaced by R1 minus 2 R2. This will make the entry in the pivot column as 0. Next, R3 has to be replaced by R3 plus R2. So, once these 3 elementary row operations are applied, we will get the corresponding entry or the corresponding column as 0, 1 and 0. So, what happens? Let us look at the next iteration. Yes, this entry corresponding to x5, this has become 0, 1 and 0, and that is what we wanted. Once this has become 0, let us observe the BFS that we have. Now, the BFS that we have is as follows: x3 is equal to 14, x5 is equal to 5 and x1 is equal to 8 and all others 0. Now, what does this mean? This means that this particular BFS is corresponding to the point C, which is given by 8, 0, because you will see x1 is 8, but x2 is 0. So, this particular BFS which we have obtained in table number 3 is corresponding to the point C given by 8, 0 in the graphical method. Let us look at the point C in the graphical method. Here it is. So, this is the point C. What do we find? In the first iteration we started with 0, 0. In the second table we got the point D, and in the third table we have got the point C. If you look at the deviation rows, we have to first calculate the deviation rows obviously. The deviation rows are calculated using the same method: 6 minus 0, 0, 6 multiplied by 0, 0, 1, which is coming to be 0. Similarly, this entry is 0, this entry is 0, this is minus 2, 0 and minus m. You will observe that this entry is 0 because it is the basic variable, x1 is in the basis. Similarly, x3 is in the basis, therefore, this entry is 0. x5 is in the basis, so therefore, this entry is 0. Minus 2 and minus m are non-basic variables and their entries are non-zero. But the most important thing is this entry, x2 is not in the basis, x2 is not in the basis, it is a non-basic variable, but it is having an entry 0. Now, this is something which needs to be taken care of, because if there is a variable which is non-basic, but it is having a entry 0, then this is an indication that the problem has multiple solutions. So, what is the indication in the simplex method to find out whether a problem has multiple solutions? Yes, the criteria to note is that if in the deviation row any entry corresponding to a non-basic variable is 0 in the deviation rows, then that indicates that it is a case of a multiple solution. So, that is what it says in the bottom line, optimum solution has been reached, but in the deviation rows the entry corresponding to a non-basic variable is 0, that is this entry is 0, and this is an indication that the problem has multiple solutions. Now, as you know, in the graphical method we have seen that C is one of the multiple solutions. How to get the other multiple solution, that is D? Now, that has to be seen, and for this what we should do is, although the stopping criteria has been achieved, but we need to find out one more multiple solution. So, we need to perform one more iteration. And how to perform one more iteration? We need to make one variable enter the basis. Now, the question is, which variable should we enter the basis? The best method is to choose this x2, because x2 is corresponding to x2 is a non-basic variable and it is corresponding to a 0 entry in the deviation rows. Therefore, we can make x2 enter into the basis. So, if x2 enters into the basis, then we need to find out the minimum ratio test, and by performing the minimum ratio test we can see which variable should leave the basis. And accordingly, what do we find? We find that this is the next table. We find that the BFS that we get is nothing but x2 is equal to 42 upon 5, which is nothing but 8.4. Similarly, the next variable x3 is 39 by 5, and the other basis is x1 is equal to 12 by 5, which is nothing but 2.4, and of course, the rest of them are 0. So, this PFS is actually nothing but the point corresponding to the point B given by 2.4 and 8.4 in the graphical method. So, this BFS is nothing but the point B, and if you look at this 2.4, 8.4, let us go back to the graphical solution. Yeah, here it is. B is nothing but the point 2.4 and 8.4. So, what happens now? This tells us that we started with the origin, that is the 0 0. In the first iteration we moved to the point D, that is 3 0. Next iteration we moved to the point C, that is 8 0, and we found that the stopping criteria has been achieved, and that indicated that due to one of the entry in the deviation rows corresponding to a non-basic variable was 0. So, this was the case of a multiple solution, and therefore, we performed one more iteration. And since we performed one more iteration, we found that the next solution obtained is the point B given by the coordinates 2.4 and 8.4. So, the solution that we obtained in the graphical method, that is B and C, has been verified. What we find? We find that not only the point B and the point C, they are the solutions, but also all those points lying between the point B and C are also solutions. Since we will note that the basic feasible solution that corresponding to the iterations in the simplex method are nothing but the vertices of the simplex that we have seen in the graphical method, what do we conclude? We conclude that there are the following two solutions. Number 1, the solution number 1 is 8, 0, x1 is equal to 8 and x2 is equal to 0, and it has an objective function value as 48. This corresponds to the table number 3 that we have just now obtained, and this also corresponds to the point C given by 8, 0 in the graphical method. The second solution is nothing but the point x1 is equal to 12 by 5 and x2 is equal to 42 by 5, and this also has the objective function value 48, and this corresponds to the table number 4, and it also corresponds to the point B given by 2.4 and 8.4 in the graphical method. So, I hope you have tried to correlate the BFS during each iteration of the simplex method as well as the points on the graphical method. So, we know that the 2 points B and C are the solutions, and as I mentioned earlier, all points lying on the line segment joining B and C are also solutions. This is the case of the multiple solutions or alternate solutions. By the way, how many such solutions do you think exist? Can you count these number of solutions? Yes, you cannot count these solutions because the value of lambda, because there are infinitely many points lying between B and C. As I mentioned in the previous slide, here all points lying on the line segment B and C can be obtained using this formula, where the value of lambda lies between 0 and 1. Since lambda is a real number, assuming values between 0 and 1, this indicates that the number of p's that are possible are infinite, and that is the reason why we say there are multiple solutions to this problem. There are alternative solutions to this problem. So, this is the case of the multiple solution, and in the end let us try to recapitulate what we have done in this lecture. We have tried to look at the multiple solution case by comparing the calculations of the simplex method along with the graphical method. We have seen how in the simplex method we move from one vertex to another vertex, and those vertices are nothing but the BFS, which are the corresponding BFS in the simplex calculations. So, finally, we conclude this lecture, and as an example, as an exercise, I want you to solve this problem: maximize twice x1 plus x2 subject to twice x1 plus x2 less than or equal to 50, twice x1 plus 5 x2 less than or equal to 100, twice x1 plus 3 x2 less than or equal to 90, x1 and x2 both greater than or equal to 0. I want you to observe this problem and you will find that the slope of the objective function is the same as the slope of the first constraint, and this indicates that the problem has multiple solutions. So, just as we have done in this lecture, we have solved the problem using the graphical method and we have solved the problem using the simplex calculations. Try to find out the movement of the vertices along with the movement of the BFS which is obtained at each of the iteration of the simplex method. And finally, in the final table you will see that there will be some non-basic variable which is having a 0 entry in the deviation rows. This is an indication that the problem has multiple solutions, and in order to get the next solution you make that variable enter into the basis and you will get the next solution. Thank you.